So welcome to lecture 4 of electric charges and field. So let us begin with a problem. An electric dipole with dipole moment 4 into 10 to the power minus 9 coulomb meter is aligned at 30 degree with the direction of uniform electric field of magnitude 5 into 10 to the power 4 Newton per coulomb. Calculate the magnitude of the torque acting on the dipole. So if we consider a dipole placed in an external electric field, so we write the expression that the torque net acting on it is equal to P cross E, that is P vector cross E vector, and it can be written as PE sine theta. So the maximum torque that is available is equal to plus PE, and it is when the electric field and the dipole moment are perpendicular to each other, that is the angle theta is 90 degree. The torque acting on the dipole will be 0 if the theta angle is 0 degree, that is dipole is aligned with the direction of electric field, or when theta is equal to pi, that is aligned in opposite way with the direction of electric field, and the minimum torque can be written as minus PE. So it is happening when sine theta is equal to minus 1, that is the angle is minus 90 degree. So all these possibilities exist. So now in this particular problem, the question is telling us that the value of the dipole moment P is equal to 4 into 10 to the power minus 9 coulomb per meter, and the external electric field is equal to 5 into 10 to the power 4 Newton per coulomb, and it is making an angle of 30 degree. So if we write the value of external torque that is created, so it can be written as PE sine theta, and the value can be written as 4 into 10 to the power minus 9 into 5 into 10 to the power 4 into sine 30, that is half Newton meter. So if we calculate the value of external torque, we will obtain 10 to the power minus 4 Newton meter. So this is the way by which we are calculating the torque which is acting on the dipole. It must be very well kept in mind that the external torque which is going to act on the dipole will try to align the dipole in the direction of electric field. Let us move to the next discussion. So we have already learned about the Coulomb's law. We have learned about the working of electric field lines and the value of dipole moment and the torque which is going to act on the dipole when it is placed in an external electric field. So the next concept which we will be discussing is going to be electric flux and Gauss law. But before going into it, let us take a few examples of calculation of electric field without using Gauss law. So we will be considering a few setups where we will try to calculate electric field due to a continuous charge system without involving Gauss law. So let us begin with a line charge. So we are dealing with electric field due to a line charge. Due to a line charge. So we are considering that there is a line charge, something like this, with positive charge uniformly distributed over it, such that lambda is charge per unit length, and due to this charge system we are calculating electric field, say at a point P which is at a distance r and is making angle alpha and beta as shown. So we are considering that the charge per unit length is lambda. So lambda is charge per unit length, So if we consider a unit charge, that is dq, at a distance y from the center, we are selecting a small patch of thickness dy having charge dq. So over here we can say that lambda is equal to dq by dy, and hence the value of dq is equal to lambda times of dy. So this is the value of the small charge dq which we obtain. Now this small charge is subtending a certain angle theta, and this dy is subtending a smaller angle d theta at the point P, such that the direction of electric field due to this dq is dE and is directed away from the positive charge. So if we break the component of dE, then this angle is also going to be theta, that is vertically opposite angle, and the value will be equal to dE cos theta, and this one is going to be dE sin theta. So if we look at this triangle, so we can consider this triangle like this. This is distance y, this separation is r, and this angle is theta. So this length can be considered as y square plus l square using Pythagoras theorem. So now I can write that the value of dE is going to be equal to k dq by the separation, that is y square plus r square. So this is going to be the value of dE, that is k small charge dq upon the distance, that is y square plus r square. So if I write along x-axis, so along x-axis the electric field is equal to dE cos theta. So if we consider dE cos theta, then we can write it as k dq upon y square plus r square followed by cos theta. Now dq can be written as lambda dy, and this expression can be written in this way: k lambda cos theta dy upon y square plus r square. Now over here we are seeing that the angle theta is also fluctuating along with y, so we need to make an integral in such a way that theta and y are connected. So over here we are using a substitution. So I am writing tan theta is equal to y by r from this triangle that we have, that is y is equal to r tan theta, and hence dy by d theta can be written as r sec square theta. So that is dy can be written as r sec square theta d theta. So we can modify this expression which we have obtained over here into k lambda cos theta dy can be written as r sec square theta d theta upon y square plus r square, so that is r square tan square theta plus r square. So we can write it in this way, that k lambda upon r, we taken out r square common, and from the r in the numerator we have cancelled out it. So we are left with cos theta sec square theta upon 1 plus tan square theta can be written as sec square theta d theta. So we are left with an integral like this, where we can again chop this out, sec square theta, and we are left with this integral. So now if we put the limit is beta and alpha respectively. So we can write the value of electric field in the x-axis direction as, so the electric field along the x-axis direction can be written as k lambda upon r sine beta plus sine alpha. So we will obtain an expression like this. So if we come back to the previous page, so we had this expression which we integrate this, putting the limit in terms of alpha and beta, and then we obtained the value equal to lambda k lambda upon r sine beta plus sine alpha. If we look at the limit over here, the clockwise is taken as negative and the anti-clockwise is taken as positive. So from this point of observation, that is point P, I can say that alpha is going to be positive but beta is going to be negative, so I'm putting over here as minus beta. So if we would have solved this integral, we would have obtained k lambda upon r. Integration of cos theta will be sine theta. So we would have obtained sine alpha minus of minus sine beta, that is it will become plus sine beta. So that is the reason why we have something like this, that is k lambda upon r sine beta plus sine alpha. If we solve along y-axis, so in the previous page, the expression of Ex, that is this expression, will change and we will obtain dE sine theta. So we will obtain Ey is equal to dE sine theta. And if we follow the same procedure, we will be left with integration of sine theta. And hence the result which we are going to obtain for the electric field along y-axis will be k lambda upon r cos of beta minus cos alpha. So we get this expression over here. So over here we are taking a note. So if the line is symmetric, that is alpha is equal to beta, so the value of electric field along x-axis will be equal to 2k lambda upon r sine alpha, whereas electric field along y-axis will become equal to 0 if it is perfect symmetric in nature. The next one is, if the wire is infinitely large, if the wire is infinitely large, then the value of alpha and beta is going to be equal to 90 degree, and hence the value of electric field along x-axis is going to be 2k lambda by r, whereas along y the value is going to be 0. If the wire is semi-infinitely large, so then the value of alpha can be 0 or beta is equal to 90 degree, and the converse is also true. So this time we will obtain that the electric field along x magnitude is equal to k lambda upon r, and so is the value of electric field along y-axis, that is k lambda upon r. So I hope you understand the meaning of infinitely large. When I say that the wire is infinitely large, I mean to say that this wire is so large that the value of this angle which it is subtending will become equal to 90 degree. Semi-infinitely large means one end of the wire is near me but the other end is tending to infinity. So this is how we obtain the result for electric field due to a charged wire. So without using Gauss law also, the electric field calculation can be attained. So now we will be understanding the concept of electric flux, and then we will be discussing Gauss law in detail. So if we come to the concept of electric flux, so the first thing that we understand over here, that is electric flux is a dot product of electric field and area vector. So that is the mathematical definition which we are talking about. So let us begin by understanding the mathematical aspect of electric flux followed by its physical significance. So if we consider that electric field is present in space and we are talking about a particular patch, so let us take something like this, that this is the area vector about which we are going to discuss about electric flux. So we are considering that the outward area vector is treated as, outward normal is treated as positive for the time being. So we are considering this as area vector and the electric field is in this direction. So we are considering this as electric field E vector, which is making an angle theta with the area vector. So the value of electric flux is written as E dot A. So electric flux is given by the dot product of E and A, which can be written as EA cos theta. So this is the value of electric flux which we have.